So, good afternoon. I'm Dr. Hina Pande from the Photogrammetry and Remote Sensing Department at the Indian Institute of Remote Sensing. Yesterday, in the first session, an overview of all the data sets, the different types of methods and techniques that can be used for documenting heritage sites, monuments, etc., were discussed. In today's session, we will be talking about optical remote sensing, which is going to focus on ground-based methods and instruments, specifically for archaeological studies. So we will be talking about how documentation can be done using these ground-based instrumentations. So let us first take a summary of what are the methods and techniques which are able to give us 3D data. So they can be categorized into image-based methods, which we call photogrammetry. These are able to give us dense point clouds or sparse point clouds, as the case may be, or the requirement. They are cost effective, but the user needs to have some experience in processing the images and extracting data from them. Then we have range-based methods. Here we are talking about optical active sensors. So we will not talk about SAR, etc., which will be dealt with in a separate discussion day after tomorrow. So these range-based techniques in the optical region would be laser-based sensors, and these give us very dense point cloud data. These data sets are called point clouds because they are very, very dense set of points which have X, Y, and Z coordinates. Therefore, we can measure objects in 3 dimensions using this kind of data. They are quick, easy to use, but they are very expensive instruments, sophisticated instruments, and sometimes some of the instruments are also bulky, so they cannot be carried easily to different places, inaccessible terrain usually. Then we can also collect 3D data or create 3D models using surveying methods like total stations, GPS, or if we have contour maps, etc. So here usually the point clouds are sparse, they have low density and resolution, and the collection is time consuming because we need to carry these instruments physically to that place and then take measurements, and the measurement or the coordinates will be measured for the location where the instrument is placed. Here also we have to be physically present at the location. However, the point clouds that we get, I will just show you a few examples. The point clouds that we get are very, very dense. So at one instance, we can capture millions of points over a small surface or a large surface, as the case may be. Then with these methods, we can also do modeling, or we can use computer graphics to generate 3D models and point clouds. So basically, range-based modeling would give us very high vertical accuracy. They will be easy to use. The option of measuring data as full waveform data. Full waveform basically means we can either collect data as discrete returns. Because we are talking about range-based modeling, it would mean that we send a pulse or a signal, it strikes a surface and it comes back to us. So if we are measuring discrete signals or returns, then we get discrete data, range data. If we digitize the entire return signal very rapidly and store it, the entire backscattered energy from the emitted pulse, then we call it full waveform data. And this gives us a lot of additional information apart from the range. For example, to study physical, for example, we can study the width and the amplitude and then do certain kinds of analysis using this data together with the range information that we are getting. Then we come to image-based modeling, 3D modeling. So here basically, because we are talking about ground-based methods, we will be specifically discussing photogrammetry using terrestrial systems or scanners, sensors. So the advantage here is that, like range-based 3D modeling, this is also instantaneous and very rapid image acquisition. The cost of acquisition is very economical, that we can do it in quite less amount of money. Also, the processing and analysis will not be very extensive in terms of computation and money. It also gives us accuracy at very high levels comparable with the one that we get with the laser scanners or range-based equipment. It is also portable and flexible. So we will see later that even with the help of your mobile phones, the cameras that we have on your mobile phones, we can capture overlapping images and then use software to do 3D modeling. The models can be created for a variety of structures. They can be engineering structures, they can be buildings, trees, or any other earth surface features. In fact, you will be surprised to know that these are widely used in fields such as the medical field. They are also used in entertainment and movie industry to create all these very high resolution gaming applications and 3D movies, etc. Both photogrammetry and terrestrial laser scanners. Those very high computer graphics, advanced computer graphics that you see in 3 dimensions are all made with the help of these kind of techniques. So we will start with image-based 3D modeling, that is terrestrial photogrammetry. Now, photogrammetry, based on where the sensor is placed and what is the distance between the sensor and the object, the camera object distance, we can categorize it as far range photogrammetry. So if I place the camera or the sensor on an aerial platform or on a satellite, that is space-based platform, since the distance between the object and camera is quite large, I call it far range. We categorize it as far range photogrammetry. And when the distance is less, that is in the range of 300 to 500 meters, then we call it close range photogrammetry. Now, as you can see, the camera axis in both aerial and satellite photogrammetry is vertical, whereas in the terrestrial method, it is horizontal. Right? So your axis systems will be placed like this. So we are measuring depth here in this direction. We are measuring height or depth here in this direction. Now, basically, we would define it as being the science of doing quantitative analysis or measurements by using photographs. So it is made up of 3 Greek words, that is photos, which means light or photons, gamma, photogrammetry, to draw, and after that we use these photographs to take metric measurements. So the primary objective of using these overlapping images is that we are able to derive precise coordinates of the points in the overlapping region of the photographs. Now, how is this done? We do this by viewing the area from 2 different view angles, and thus we recreate same conditions as they must have been when the photograph was taken. So an impression or a virtual 3D model is created with the help of the instruments or with the help of software. If you notice that in everyday life also we use 2 eyes to look at objects and then we get depth perception. So the same concept is applied here. We need at least 2 images from different angles or positions so that we are able to create a 3D model. If we have more exposures, then also it will be a very good method to create these 3D images. So this is how the principle works, that you use 2D images. Individual images are 2D. So the image A or the left image has been taken from this location. This is the object. The second exposure is from this location, and wherever there is an intersection, for this point, a 3-dimensional coordinate can be measured. Right? So what we need is camera position and camera orientation at the time of photography. So this has to be recovered, and this is done with the help of orientation and image matching methods. These are mathematical methods, equations which are solved. So this gives us the location of each camera's perspective center, and it also gives us any orientation or rotation details of the camera. Then once we do matching, then the location of the point on each image sensor is also retrieved. So the same thing happens in the human brain also. When we use two eyes as sensors, we are looking at the object on the ground from two different locations because there is a distance between the two eyes. So two locations we get image, and in the brain an inverted 3D image of the object is formed. Now when we are doing terrestrial photogrammetry, suppose this is the object, so we can do it from multiple locations all around, covering the entire object. If possible, we can also cover the top. So maybe if we have a UAV, or if we have a ground-based system, a crane or something on which we can mount a camera, then we can take images of this from the top as well. And then because these will all be overlapping and they are multi-station exposures, all the rays will be converging, and we will be able to make a 3D model like this. We can then use instruments or glasses, etc. for visualizing it in 3D. You must notice here that if you recall, when you go to a 3D movie theater to watch a 3D movie, it is something like this that you see on the screen, and then you are given glasses to visualize it in 3D. So your left eye looks at the left image and the right eye looks at the right image, and a simultaneous view gives you a virtual three-dimensional model of the object like this. So this is a virtual model that can be created with the help of at least two images, but if we have more multi-station exposures, we can create a 360 view. This example shows the Buddha Tower in Angkor Wat in Cambodia, a very well-known heritage structure. Similarly, here if you see, these are several of very well-known heritage structures, internationally well-known structures, and you see all these camera stations are positioned like this from all around. So this is a church in Ethiopia, a very, very ancient Christian church, which has been recorded and visualized. So a very detailed 3D, this is a 3D model. Now, along with the 3D coordinates, images have also been captured. So the images have been superimposed on the 3D model or on the wireframe. A wireframe would be something like this. This is a collection of 3D point clouds. This is the actual data being captured, and this is the instrument. So this is another example of a church here. So here we were talking about we can overlay or superimpose the photographs as textures. So this will give you photorealistic models. So you see each and every detail in very high resolution. So any damage or any change in the structure, etc., can be easily monitored and changes can be detected. Similarly, the same kind of thing has also been done for documentation of the Bamiyan Buddhas. So they were all caves all along the mountainside here. So you can see there are several such pockets in which the Buddha statues were there. So this has been done using satellite data. So the locations of these caves have been identified, and then 3D models, etc., have been created inside the niches. Now these are the statues here are missing. So if we had pre-event images and current date images, change detection can be done, and people have also tried to virtually recreate these models to scale and metrically very precise models, so that if at any time there is an option to reconstruct these, that can also be taken up. Similarly, because we are able to get very high resolution images and 3D data, so very small or minute faded details, if they are there, like these pteroglyphs or paintings or carvings on the rocks or on surfaces, these can also be studied to scale. So 3D models can be created, high resolution images can be captured, and then these can be virtually documented because these are open to the elements. So there will be high amount of weathering, etc. And we might lose these very important ancient cultural heritage structures or paintings or hieroglyphs and so on. So documenting them and preserving them is a very important task. So these ground-based techniques are a very good method because the space-borne images or satellite images may not give us the resolution required for documenting them. However, their locations can also, we can use many types of data in conjunction to have a very comprehensive documentation. Similarly here, because it is a very fast method of modeling, now if you see here, very detailed models are made. So any small changes can be detected. So here you see this is a shaded 3D model from the camera positions. Now if you see here, there are 2 million points here and 20,000 edges. So for this very small object, dimensions are 3 meters by 1.5 meters. So within this area, 3 meter by 1.5 meter, there are 2 million points. That is, for 2 million points, I have X, Y, and Z measurements. And after I get these points, I can do with 6. They are saying that they have taken a total of 6 images. So a very detailed 3D model can be created. Then we can superimpose 3D textures on these models as well. So this is an example from Mexico. These are photographs. Again, very, very minute details can be seen. So here you can see they have taken 5 images and some 900,000 points have been captured here. So a very, very detailed. So if there are any breakages or if there are any changes in the structure, some moisture is there or some part has broken off or there is a crack, all these details can be seen and measured using these very high resolution images. Since we are also making 3D models and we are texturing them with the images, and if we keep doing it, documenting it over fixed periods of time, we can also see the change that may have happened. So we can do change detection also. Similarly, the size of object is not a concern. A very small object or even a very large site which extends for kilometers can be covered with the help of these methods. So if you see here, I had in the previous slides also, I had given you an example of the size. So 3 meter by 1.5 meter. And here it is even smaller. So it is a small statue of about 50 centimeters by 40 centimeters approximately. So you see a very, very small structure, but the detail that you can see here in different position, very small details, each curl of the hair, the ears, the folds in the cloth, all these details are very well visible. So if you see here, total number of points that have been captured here scan is around 5.6 million points. So 3 million triangles were made to do the modeling, and here we are also seeing based on height they have given it different color. You can also give it the actual superimpose the actual colors using the RGB information from the images. Then this is another example. So this is a small brick which has a carving. So each small detail, as you can see, is visible. Any change will be easily recognizable. It can be documented, and then it can be studied by people who are experts in who either want to study the structure itself, or if they want to study the or analyze it for virtual preservation. They want to make it as a sample in a library and see how they can, if there is a damage at a later stage, can they use this virtual model for preservation or virtual reconstruction purposes. So if you want to make digital museums, etc., these models will also be very helpful. Now I will quickly demonstrate to you some case studies that we have done here at IIRS using terrestrial photogrammetry to showcase what you can attempt with the help of this technique. So these are reconstruction of few heritage sites which are of local importance in the town of Dehradun. This is the clock tower. So this is a wireframe model, and it is to show you that these were where the camera stations were positioned. The wireframe model was generated, then a shaded 3D model was made, and with the help of this, the RGB information and the image textures were superimposed on the model. So then several other analysis was also made because there are several kinds of damages. Those damages were documented and studied, and a 3D model, virtual 3D model was created for this purpose. Similarly, this is another archaeological structure, heritage structure, which is called the Gillespie's Monument. So here you see the camera positions, wireframe model, shaded model, and then the textured model. Now these are fairly simple shapes. However, we can also attempt to do it for more complex shapes, as you can see here. So this is a Buddha monastery temple in Dehradun. It's called the Mindroling Monastery, and there are temples and statues here. So this temple was documented both with the help of photogrammetry and with the help of terrestrial laser scanner. I will show you to you later. So the camera stations were positioned in this way. Each small detail is being, so even the small tower here can be, the structure on top of the tower is documented. And the other advantage is that because these are taken with metric calibrated cameras and instruments, laser scanners, we can also take use these to be taken for very precise measurements up to, depending upon the resolution at which the data has been captured, we can go up to millimeter level measurements. Now this is how the raw point cloud would look like, and when we superimpose the image textures on top of this data. Similarly, the Forest Research Institute, which is also a very huge heritage structure, about 200 years old in Dehradun. So here, because it is a very large structure, as you can see, and very complex also. So around 56 photographs were used to capture the entire building. Since we did not have any way in which to capture the roof, we were not able to capture the actual roof texture, but a simulated roof texture was used to recreate the top part of the building. Now, as you can see, a photorealistic reconstruction is shown here in high resolution of a part of the building. So you can see pillars, windows, the window bars, all small details of the arches, bricks, etc. So any kind of damage or any other detail that you wish to capture and document, that is possible with the help of these kind of documentation methods. Similarly, see 3D reconstruction of the buildings in the campus of IIRS was also done. So this was done some 8-9 years ago. So there are a lot of other buildings and structures that have come up. However, it is just to demonstrate to you that one can create a very realistic walkthrough or virtual representation of these structures. So each building, if we zoom in, then each small detail of the windows, the railings, everything will be very, very clearly visible here. And we can create a virtual walkthrough. One can also add virtual reality or augmented reality and create a 3D view, which you can use as tourism, virtual tourism, or virtual museums, etc., for statues and paintings and things like that. So it can be used in various ways. So here are some zoomed views of the structures that were here. So if you see, this is the Godavari hostel building here, and if you see it here, each small detail in 3 dimensions is visible. These models can also be put up on the web portals. As you can see here, the FRI model has been placed on the Bhuvan web portal, so people can visualize it on web portals. We can put it up on Google Earth. The Bhuvan web portal example is here, and all these other models were also superimposed there, so you can get a virtual tourism application for these. Then here, an application to see that how we can use low cost instruments like mobile phones. An application was developed at IIRS called Trivim. It is an open source application, and it uses GPS enabled cameras or smartphones to create georeferenced 3D models. And what we require is that you need to have overlapping sequence of photographs. We also require location of camera stations, which we can get with the help of the GPS, and a user-defined database structure to add information about the object that we are looking at, so that we can do a query if required, and footprints of buildings. So the output here would be georeference 3D model with an attached database. This can be done at sub-meter level accurate. We can create 3D sub-meter level accuracy. Floor-wise database can be attached and stored, and a query can be operated on the database. It is a very low-cost method of creating 3D models of built structures. So here, as you can see, this database is attached, and point clouds can be created, and then you can create 3D street views and so on. So it can again be used for various applications, for urban application governance, or for development purposes, or if you need to have database. Similar things can be used for heritage structures also. Now with this, the first part of the discussion focused on image-based methods. So you had to capture overlapping images to create 3D models. Now we come to the next section, which will be ranging method, that is LiDAR sensors or laser sensors for capturing 3D information. So it is a laser-based remote sensing technology, and as we know, it is a small laser is pointed at a surface, and it measures the time that it takes for the laser to return to its source. Reflects back and is measured again by the receiver. It is an active sensor, and it gives very precise information about the target. Now the advantage is that because it is an active remote sensing method or a sensor, it can be done during night or day, and it makes vegetation possible because it penetrates vegetation. So it can give us data beneath the vegetation also, which the passive sensors or image-based technology is not able to do. So in low contrast through vegetation, and also in shadowed areas or in places where there is low contrast. Please remember that when we are taking photographs, we have to be very careful about the illumination conditions. So if it is dark or it is cloudy, then the quality of the images that we capture will not be very good, and then image matching will not be very accurate. Okay. So this technology is used to produce digital elevation models for 3D mapping, and it gives us very, very dense data. So as you can see, we can measure multiple returns from this method, and since vegetation canopy can be penetrated, we also get some amount of data from beneath the canopy in even very densely vegetated areas. Right? But it is a non-imaging sensor. So unlike photographs, it does not give us an image, it only gives us point data, that is range information, which means that each point that is measured has X, Y, and Z coordinates associated with it. So LiDAR platforms can also be ground-based. So we can have terrestrial laser scanners, which can be static or mobile. Static would mean that I place it at one location and take measurements. A mobile sensor would be that you mount it on a moving platform and then take measurements, or you carry the sensor yourself and take measurements while in mobile mode. We can have airborne sensors that they can be manned. That is, if I place it on an aircraft. They can also be unmanned if you place it on a drone, etc. Laser sensors are also available on spaceborne systems. A few examples are the ISAT. Chandrayaan-1 had the LLRI. Then there are several others like the LIGHT, SLA, Calypso. The recent one is JEDI, which is placed on the International Space Station, and it gives us full waveform data. The ISAT-1 also gives us full waveform data. Currently, ISAT-2 is operating. So the data acquisition using the terrestrial, since we are discussing only ground-based sensors, we will focus on the terrestrial laser scanning data acquisition. So the laser emitted from the scanner hits the object and is reflected back. So the time of flight is calculated, and with this X, Y, and Z coordinates are calculated with the help of this time. It is a non-contact surveying method, and it gives us millions of points in just a few minutes. Now the entire region inside a user definable window is scanned in very less time, and even though the time taken is less, the accuracy comes out to be very, very high in the range of millimeters or centimeters, depending upon the specifications that you have used during the time of data acquisition. So the broad methodology would be that you plan your data acquisition, collect it using laser scanner or GPS and photographs. The laser system is a combination of a laser scanner, a GPS, and a camera. So we get all the three information as one calibrated data set. Then we can register and georeference. Then one has to do, of course, editing and cleaning, etc. We make the point cloud ready for use. And then it can be integrated with other kinds of data sets, or some analysis can be done using for modeling or for surface modeling or photorealistic modeling and so on. So co-registration of data is very, very important because we are going to be using several scans, right? We can also integrate the point cloud that we get from laser scanner with close range photogrammetric point clouds. So we acquire the two data sets and integrate it with the color. The color is taken from the photographs, and the X, Y, and Z coordinates are taken from the laser scanner. And there are several advantages, as we will see. The point cloud from the TLS and the images from the CRP. Also, the two point clouds can also be separately integrated. Now, this is to give you an overview or a feel of how the lasers, this is raw data as taken from the scanner. So if you see, no color has been added yet. The text, color, texture, or RGB information is not added. However, it is only the point clouds, but there is no image, please remember here, only points, very, very dense point clouds here. So if you look at this zoomed portion, the smallest details can be seen here. Yes, each window, the balcony, even from a distance, the scanner is placed here, but we can look at the staircase, the railings, etc. in very high amount of detail. So similarly, we can do large scale cultural heritage sites also can be covered. This is the Machu Picchu site. Then small objects can also be covered. Pteroglyphs can be covered, which are dull, small, very light markings on rocks, etc., surfaces, etc. And with the help of these, we can then create 3D or 4D city models. If we have time component with us, we take multiple scans at different times, then we can monitor it over a period of time. Now, to give you an example of how laser scanner data is acquired. So several scans for this church in the nearby vicinity were done. This, as you can see again, this is a photograph and this is the laser scan, no image. So, but it almost, the point cloud is so dense, it appears to be like an image. Now here it is displayed at different scanning resolutions. So at 5 points at every 5 millimeters, points at every 10 millimeters, and points at every 20 millimeters. So rasterization has been done at different levels. And as you can see, the 3D point cloud can be visualized at different resolutions, and different databases can be created, and with the help of these damages can be detected. So if there are cracks, etc., one can look at it. Similarly, this example was also shown to you with the help of close range photogrammetry. Now the same area has been covered with the help of terrestrial laser scanner, and this is how the data will look like actually if you zoom in. So you can see each individual point, and each point is associated with X, Y, and Z coordinates. So in the magnified view, you can see there is no image, only a collection of points, and this is called a dense, ultra dense point cloud. So here you will appreciate that each small detail of the railing, etc., is visual. We can visualize it. Changes in each of the carvings, etc., can also be seen. If there are fading in terms of paint or breakage or cracks, all these can also be visualized. Now if you appreciate this small zoomed in area of the face of the Buddha, you will see that each small, it appears to be almost like a photograph. However, it is only a collection of points, as I keep telling you. So each small detail of the curls in the hair, the eyes, the eyebrows, everything is visible in very high amount of detail. So the example of doing this kind of documentation and what we can derive from it, one can use it for damage detection. So the example of the clock tower is displayed here. Now here the structure was unrolled so that you are able to see at one instance the entire structure, and where the objective was to see where there are damages, cracks, etc. So here one can see, you can create a database at different levels. So if it is a very minute crack, then you would be requiring data at the highest level, and if it was data the crack is quite large, then we would also be able to see it or visualize it at a coarser level. So one need not extract the entire point cloud at one go. To simplify things, one can use small tiles from the database, access small tiles from the database. Then we had also come up with a small prototype framework, which we call Dharohar, wherein we can do a little bit of processing of the point clouds and optical data for heritage and archaeological restoration. So there are some image processing methods that can be done, some photogrammetric and laser scanning operations that can be done. And if you have two-time data, that is the pre-event image and the post-event image, and there is a crack which can be visualized. So the change can be seen here. Now, for some time, IIRS has been involved in 3D digital documentation, damage assessment, and reconstruction of cultural heritage sites. These were the examples that I showed you were pilot studies that we had done, and then we thought we would put this the information gain that we have had and the knowledge that we've gained through these small studies to larger perspective, and we attempted to document UNESCO World Heritage Sites in northern India. My colleague tomorrow will also be giving you a detailed description of these studies. However, I will just give you how. So the attempt was to create comprehensive digital documentation methodology and to create a database, to have architectural primitives stored in a database, if one can attempt 3D blueprinting and damage detection and virtual reconstruction. In addition, we also attempted conjectural reconstruction. So all these will be shown in detail tomorrow. And the study sites that we attempted were UNESCO heritage sites in Delhi and Bihar. So this is the kind of data that we can get. Here again, we used both close range photogrammetry and terrestrial laser scanners to, and then integrated the point cloud to get the complete structure. So this is Qutub Minar, this is Humayun's tomb, and this is Nalanda Mahavihar. So that is why that is how we were able to integrate data from multiple sources and multiple platforms. So here people can also add, we have not attempted it in this study, but you can also add UAV data and do photogrammetric processing of that data and add that. So that adds another perspective to this. These are again some few examples of how the laser scanning data can be captured for different structures. Now, if you will appreciate, all the small carvings and the small details, etc., are all very well visible. Also, we can do scanning for both the interior and the exterior. So we have a entire structure, so we can do digital blueprinting. The similar data capture can also be done using spaceborne data. So some components can be captured using the spaceborne data also. So here you can see of both interior and exterior, a photorealistic walkthroughs can be, these are again, please remember, no images, these are not photographs, these are textured point clouds. And these are screenshots of walkthroughs that I have displayed here. So this is only a textured point cloud, that is RGB or color information has been taken from the images, and this entire display here, either of the interior or of the exterior, is only point clouds. Similarly, if so, you see at what high resolution and what amount of detail can be visible. So even if there is a very, very minute crack in millimeters, that will also be detected here, and it can be monitored over a period of time. Statues, small objects, etc., can also be seen. I will skip through these because these will all be shown tomorrow. So if you see here, small objects also can be done through the 3D heritage documentation. So with this, we come to the end of this session, which focused on ground-based methods for documenting heritage structures, specifically built heritage structures. You must have gone through the Niti Aayog recommendations for the working group on monitoring and documenting heritage structures. They have strongly recommended the use of technology like photogrammetry, laser scanners, UAV platforms for making comprehensive documentation of different kinds of heritage structures so that they can be monitored and preserved for the coming generations. We will now be taking up questions.